Welcome back to Physics of Music. So today we're going to talk about some really important ideas for how to understand the way that musical notes are built up from simpler sounds. And before we get into that, I'm going to have a quick review of what we talked about in the last video. And so the very important idea that we discussed was that if you have any sort of sound, then what determines the thing we will hear is basically just one physical thing, and that is this time graph of the displacement of air as a function of time at the location of our ear. So this is an example where we hit a cymbal and the air near the location of our ear would be displaced in this way. It's still, and then it oscillates back and forth a little bit, and then it's still again. And so for any kind of sound, whether it's a simple hit of the hi-hat like this one, or an entire orchestra playing, you can make one of these time graphs. And the time graph has the full information about the sound that that ear is going to hear. So I wanted to just do an example quickly to show you what this looks like for a short piece of music that I'll play. I'm going to play a little bit of Over the Rainbow on my recorder. Apologies for the playing. So here we go. Okay, and so this is the time graph, but it's really compressed. And in order to see the features of that, what we need to do is zoom in. So we can zoom in here quite a bit. And so there you see that you have a nice periodic time graph. And so that corresponds to the fact that I was playing a musical note. And then if I jump ahead, we see that, okay, it all looks periodic. Sometimes the amplitude is higher. So this is the part where probably I was playing that high note and it was louder. So you see that there was more displacement there. It was a higher pitch, and that corresponds to the fact that these peaks are closer together. So shorter period, faster frequency. Let's actually try to play this and see if it, so we'll play it at the same time. Hopefully you can hear it and see it. Okay, and so that information in the graph is actually enough that tells you not only what notes I'm playing, but how they sound and how loud they are. And so in particular, if we wanted to, we could use this information to play back the song. That's what we just heard. I didn't play the recorder again. I just told the computer to take that time graph and turn it back into sound. So you might be wondering, how does that work? And so just as an aside, I'll mention the basic idea behind speakers or headphones that are able to play back music. And it's a really simple idea. So you remember that the way that we made that time graph was to use our microphone. And the microphone had a membrane that just vibrated back and forth in response to the changing pressure of the air. So the displacement of the membrane in the microphone is basically the same as the displacement of the nearby air, or it's very closely related. And so in that way, we're able to kind of store the information about the displacement of the air versus time by just turning the motion of that membrane into some electrical signal, and then the computer has some way of storing that. And so the speaker is just a reversed version of that, where we take the information in this time graph that is stored somewhere we convert that into an electrical signal that's sent to a speaker, and some very simple system of just some wires and magnets that we'll talk about later in this course converts that electrical signal into a moving object, and then that object displaces the air. So this surface moves back and forth in the way that is specified in that time graph. It displaces the air in just that way, and then it produces a new sound wave, which is going to be just like the sound wave that was recorded by the microphone earlier. Okay, so if we have this object inside the speaker, and if that moves in such a way to displace the air in the same way that a tuba would displace the air, then it will sound like a tuba. Okay. So I want to get back to talking about musical notes. Those were particular sounds. We saw an example of that in the recording I just made. And the way that you can easily tell that there's a musical note being played, given the time graph of the displacement for the sound wave, is just to look for those repeating patterns. So when you have a periodic repeating time graph, then that's going to be a musical note. And the frequency of that note is just related to how often this thing repeats. Okay, and so we have that property, that the frequency is related to like how often this repeats. I guess in musical terminology, what we're talking about is the pitch of the note. Okay, so we have this one property of notes that they could be higher pitch or lower pitch. And so that is the thing that's related to this mathematical concept of the period of the displacement time graph, or alternatively the frequency, which is 1 over the period. What are the other features of different musical notes that distinguish them from each other? Well, one of them is the loudness, whether is it a loud note or a soft note. And then a third one, which is the most complex of the three, is what does it sound like? What are the other qualities of the sound other than pitch and loudness? So does it sound like a trumpet or a cello? So that character of the note is what we call the timbre. And what I explained last time was that we can understand all of those three features through features of the periodic time graph that represents the musical note. The louder note would correspond just to a larger amplitude. So we could just imagine stretching the graph vertically, so a larger displacement of air, but in the same kind of pattern and at the same frequency. If you took that time graph and compressed it in the time direction, so everything is happening faster with a smaller period and a higher frequency, then that results in a note that sounds higher to us. It has a higher pitch. And then finally, we could imagine taking the shape of what happens each period and changing it somehow. And that, of course, you could do in an infinite number of ways. And the result is that you get a note that has a different timbre, it has a different character. And so whereas this one I took from a note on my alto saxophone, this one might be a different instrument, would sound like a different instrument. So let's have a look at an example question just to give you a simple example of interpreting something from the time graph of a musical note. And so this is the graph of a note that I played on my alto saxophone. And the question is, which note was I playing? And since the graph contains the complete information about the sound, then you should be able to figure out which note it was. So maybe pause the video, read through the choices, and see if you can work it out, and then we're going to talk about it. Okay, so the key thing here is that we're just going to figure out which of these frequencies our note corresponds to. So we understood that higher pitches correspond to larger frequencies and smaller periods. And you don't really need to know about the names of these notes. This is this note is like the second G on a piano, I believe, and the third lowest D and the third lowest G. But for this question, we just need to know that those specific notes have a particular frequency associated with them. And to answer this question, what we have to remember is that the frequency of a note is just related to its period by the relation that the frequency is the inverse of the period. And the period is something that we can easily read off from the graph. Okay, so the period is how long is it before the whole pattern repeats. And we see that that is, in this case, 0.005 seconds. And so in this case, we can then figure out the frequency by taking 1 over 0.005 seconds, and we can work that out, and it turns out to be 200, and the units are hertz because we have seconds on the bottom, so that's inverse seconds or hertz, 200 repetitions per second. And so the answer to this one is C, that it was a G. So in the next video, which is going to be a really important one, what we're going to talk about is how we can make sense of these different shapes that correspond to the different qualities of musical notes, the different timbres, and these shapes that distinguish a piano sound from a trumpet sound. And it looks very complicated to describe the features of a time graph like this. But what we'll see is that there's actually a very nice way to represent that information. And it has to do with the idea that any complicated time graph like this can actually be represented or decomposed as a sum of these pure wave, these simple kind of pure wave time graphs with different amplitudes and frequencies. And so we'll start to understand